Our second topic for the week is deserts and the wind. Now, this can cause a little bit of confusion. If you look at this slide, at the bottom, you'll notice geologic agents, running water, and the wind. And one of my favorite questions when people think about deserts is to ask, what do you think is the most important geologic agent in most deserts? And people always go to the wind because they think of sand dunes. But that's actually kind of an unusual feature in a lot of deserts. You have to have a really big supply of sand and some other conditions. It turns out that running water, even though it's not nearly as frequent, is the most important geologic agent in deserts. But we've already talked about running water. We talked about rivers. Why is running water? Why are rivers so effective in deserts? Because of the lack of vegetation. So when you don't have a lot of vegetation, it's much easier for the water to come through and do its work. So you don't see a lot of rivers with water in them in the desert, but on the occasions when it does rain, those rivers are very, very effective. So I just want to clear that up at the beginning. That's not a question on the exam, I don't think, but it's something to keep in mind when we talk about deserts. A lot of times what we focus on in deserts are the features that we can see there very easily, and so that's why we think of them and talk about them when we talk about deserts. So briefly, where do deserts come from? Deserts mean low rainfall. And deserts occur typically in places where the air is very dry and doesn't have moisture. There are a couple of reasons why this occurs. Globally, if you look at air circulation patterns, and that's what you can see this picture of the globe, and you can see the air circulation patterns. Air rises near the equator and roughly 60 degrees north and 60 degrees south. In places where the air is rising, it tends to be wet, so we have rainforests or wet climates at least. That's the kind of climate that we have. We're close enough to 60 degrees north. We get a moist climate. You'll notice also where air sinks on this diagram, which is roughly 30 degrees north and 30 degrees south. Also, what they don't show you on here is it's at 90 degrees north and south, so at the poles we have air sinking as well. At those latitudes, the sinking air doesn't have a lot of moisture. Remember, it lost its moisture when it rose, right here and here. And so when it comes back down, it's dry. And it's looking to pick up moisture as it sinks and warms up. And so that's where we tend to find deserts. The Sahara Desert is right here, hovering around 30 degrees north. The Kalahari Desert is right here, around 30 degrees south. If we went around through Asia, we'd find the Gobi Desert. If we come into the Americas, we find the deserts in the southwest United States and northern Mexico are associated with 30 degrees north. The north and south poles are also considered deserts because of the very, very dry climate. So that's where we get deserts. So what do we see in deserts? What do we see because of this lack of vegetation? Well, what we find is that wind is much more effective when you don't have vegetation. So just like the running water is going to be more effective, wind is going to be much more effective in the desert. So let's talk about how wind erosion works. That's what our focus is going to be. And we look at this picture here. This is something called desert pavement. You'll notice that this area of the desert is covered by gravel. Looks almost like a parking lot, except for the fact that there are cacti kind of sticking up in the middle of that. But how do we do that? How do we get this gravel? Well, it tells us a lot about how the wind works. The wind is really good at moving small stuff, but it's not very effective at moving large materials. So what can happen over time is that the wind can move away the dust. Remember from running water, we had the suspended load and the bed load? Well, the wind has a suspended load and a bed load as well. The suspended load is what we call dust. It is material the size of silt and clay. And the bed load tends to be sand. Well, that's what the wind can remove. What's left is gravel. And so this deposit is what we call a lag deposit. It's due to something that we call deflation. And basically the wind has taken away all the material it can move, and what remains in this case is simply gravel. So this deposit is simply what remains after the wind has removed the suspended and the bed load. So there's our suspended and bed load. How does that work? Well, deflation works because the wind, if it's strong enough, can actually just pick stuff up and start to move it. The wind is not very good at actually breaking apart larger rocks. So if we look at this picture, dust in suspension, sand grains kind of bouncing along the ground, and look at this. What's happening here? Well, those sand grains bouncing along the ground, sometimes they can get picked up as high as a foot or two. They sandblast anything that's in that zone. I could probably find another picture that shows you a rock where only the bottom, like 1 foot or so, has been eroded because the sand being bounced along the ground is doing all the work. And once you get above the level of where the bouncing sand is, you simply don't get very much erosion. So the wind erosion in this case is through abrasion, but the abrasion only occurs if there is some sand being pushed by the wind. And so it tends to be very focused at the ground level. So what happens to the dust? Well, the dust can go incredibly long distances. This shows a dust storm, also known as a haboob, I think this is in the southwest United States, but it could be really in many of the dry climates on the planet. You see these giant dust storms blowing up. This dust can be moved around the planet. Dust from the Sahara Desert, because of the prevailing wind direction from east to west at that latitude, dust from the Sahara Desert ends up in the Caribbean. It ends up in South America. That dust helps fertilize the Amazon rainforest. And it ends up even in Mexico and the southern United States. So once dust gets picked up, it can move great distances. And so that ability of the wind to move its suspended load is just really amazing. It's remarkable. So we're talking thousands, and in some cases tens of thousands of miles that the dust can be moved. What does it look like when it settles out? It looks like this. So this is a wind deposit of dust. We call it loess. That's a German word. It turns out that if we go way back to glaciers, something that we didn't mention that relates to this wind deposit is if you look at in front of the glacier here, there really is not much vegetation. And again, that's partly we've got a cold climate going on here. We've got a lot of sediment coming out, so this is a sort of a floodplain. And so in the winter, when the glacier freezes, this outwash deposit in front is exposed to the wind, which will then pick up the dust and carry it away. If you do this on a continental scale, so if you think about the big glaciers that were in front of, or that came down from Canada and into Illinois, that outwash ends up here coming down the Illinois and Mississippi rivers. In the winter, when those rivers froze, the dust was blown back across Illinois, and we actually have some pretty thick deposits of loess here in Illinois. So we can find loess deposits like this next to the Mississippi and Illinois rivers, and then they thin as you go to the east as the dust was dropped out. But even here in LaSalle County, we find a foot or two in some places of loess. So that's our dust deposits. Well, it's time to move on to the big one, the sand dunes, which is what everybody's thinking of when we think about wind and deserts. And so here's our sand dune. So the dust gets taken far, far away. What happens to the sand? Well, remember, the sand is bouncing along the ground. The sand is bedload. So we can't just pick it up and drop it somewhere. And if we want to build a deposit like a sand dune, you need a ramp. So the windward, or the upwind side of a sand dune, has a fairly gentle slope. It allows the wind to bounce the sand up the side of the dune. And then when it gets to the top, it's out of the wind, and so it just slides down what we call the slip face. If you go into the lab and make a pile of dry sand, you'll find that it has what we call an angle of repose of about 34 degrees. And so the slip face of a sand dune, guess what, has that angle of repose of about 34 degrees. And so the sand is just kind of slowly sliding down that slip face and building up the sand dune. And you can see it makes little layers inside the sand dune as the slip face grows. Well, what does a slip face look like? Well, here's a picture of a slip face. There's the crest of the dune. We're on the downwind side, and you can see evidence of the sand kind of tumbling down the face of this sand dune. Now, the interesting thing about this sand dune is that this sand dune is on Mars, and this is one of the Mars rovers, and this is a picture that it took. So you can see that this process is not active only on the Earth, but it's active on Mars as well. If these sand dunes get buried and turned into stone, the slip face is still preserved, and so these are what we call crossbeds. This is evidence that there was a sand dune here that migrated from right to left across the photo. In fact, there were several of them. You can see more crossbeds down here. If you measure that angle, it's about 34 degrees. And so this is what happens as you continue to add sand in this situation. The dunes will grow along the slip face and create these features that we call crossbeds. So that is our dune story. We got a couple minutes left, so we want to hit on just two more slides. One of them is another desert feature, which is a dried up lake. So in some desert areas, the water cannot leave. It's a closed basin, and the water evaporates and leaves behind whatever was dissolved in the water. And so this is what we call a playa lake or a desert lake. In this case, it has evaporated. You can see some mud cracks there as the muddy sediment contracts. And then we see crystal growth as the water evaporates and leaves whatever was dissolved in the water behind. And that material will typically form mineral crystals such as gypsum and halite. So that's an isolated lake or lagoon. It creates what we call evaporite deposits when we get to looking at sedimentary rocks. And then last but not least, I meant to talk about this last week. It's just one slide, but next to rivers, so we're going to completely the opposite of deserts. We're going back to water. We might find a swamp. This is a picture of a swamp. One of the interesting things that happens in swamps is that we can get a large, thick accumulation of organic material. When the plants in the swamp die and the material that makes them up sink to the bottom, because of the low oxygen condition in the water, the organic material does not decay. Instead, it accumulates. It starts out as something we call peat, And as it gets compacted and compressed, it turns into coal.